Okay, so today we have as our guest Sri AravindaKrishnan Thyagarajan. Sorry for my complications with the name. And he's a lecturer at the University of Sydney and is visiting us. And I mean, he did his PhD in Germany in the University of Erlangen-Nuremberg, and then was a postdoc at Carnegie Mellon University in the US and also in entity research in the US as well. And he works on cryptography blockchains. He'll be present something about cryptography meeting game theory, how do you use this, combine these ideas for doing fair exchange. So welcome.
Thanks a lot, Rafael, and yeah, thanks for inviting me, and yeah, thanks for joining all the online participants. Yeah, so all right. So I think Rafael already gave a brief timeline. So I'm new to Sydney. It's been three to 4 months that I've been in Australia, and Sydney included, and this is my first time in Melbourne. On the contrary, I like the weather. I like cloudy, a little bit of rainy weather. Yeah, so yeah, you don't have to feel like you have to complain about the weather. I really like it. So all right. Okay, all right. So okay, so briefly, so my purpose of being here today with you all is to kind of introduce myself, tell what I work on. I know a lot of people here also interested in cryptography and blockchain-related ideas and projects. So it's the goal here is to kind of interact and kick something up. You know, all right. So my work is broadly it's on distributed applications, or on as you call it in legacy terms, it's multi-party computation. And the goal is to achieve these 4 elusive properties of security and privacy, fairness, efficiency, and scalability. All right. And the tool sets that I'm mostly interested in using to achieve these properties are going to be cryptography and game theory a little bit. So yeah. All right. So to people who are not heavy on cryptographic background, so what is distributed applications? It's a set of parties coming together. They have some private input, and they want to run an application among themselves. All right. And you have this this happening every day in your life if you're using a laptop or a computer or a tablet, or if you're connected to the network, you are already part of a distributed application, right? So you have messaging, digital payments, cloud computing, cloud storage, AWS, whatnot, okay? All right, so what do the users of these applications want? As I said before, they want these 4 properties, all right? So what does security mean? Security says that you're not revealing unnecessary information during the computation, which is closely related to privacy. That says you're not, giving away sensitive information about your personal data, date of birth, or I don't know, yeah, something like that, banking password or whatnot. All right, so then you want fairness. What is fairness? Fairness has multiple definitions. If you are from different fields of computer science or economics, you have different definitions of fairness. But the fairness definition we will go for today is that the honest participants in that application are not harmed. And we will see a more clear definition of what harm means, okay? Okay, efficiency goes without saying, is the easiest to define among these properties. Is that the application should be executable even if you're having a small phone or a minimal computing device. And scalability says it's that even if you have millions of users participating across from different continents, you shouldn't feel the lag in your application, right? Perfect. Okay, so I've set the ground. Okay. All right. So all of these properties are trivialized if you have a trusted entity that's going to support your application, right? So you just send your private input to this trusted entity. It computes whatever needs to be computed locally and just gives the output every month. And you get all these properties instantaneously, right? But it goes without saying the problem is a single point of failure, right? So if it's going to be a denial of service, or it's a compromised entity, or if it's a write out malicious entity, right? You lose all of these guarantees immediately. A simple example to see is the case of digital payments, which is also my way of motivating into blockchains, as many people would do. So in the case of digital payments, you have users who want to make a transaction among themselves, and the bank, right, is going to keep a balance sheet, and that's going to keep track of each user's balance. And when a transaction happens, the bank is entrusted to adjust the balance, all right, accordingly. And you lose all guarantees if the bank is either compromised, hacked, or straight up behaving maliciously. And we have numerous cases of data breaches and attacks that we have already seen. And this extends to beyond payment applications. Whenever you have this trusted central entity, you run, you may get efficiency and scalability, quite easily, but you are at risk of every other property that users care, right? Okay, all right. So today we will look at a very basic distributed application, right? It's not having multiple users or whatnot. It's just two users, all right? And what they are interested in is to do a fair exchange of the data that they hold. So here you have on the left, you have this red user who I will call Alice, and the Bob on the right. So Alice starts up with some private input. Bob starts up with some private input. They run a protocol pi, whatever it is. It's an interactive protocol. And at the end, Alice has to learn the private input of Bob, and Bob has to learn the private input of Alice. It's a simple exchange. Okay? Okay, so but we want this exchange to be fair. Okay, so there are two notions of fairness here. The first one is game theoretic, right? And the second one, okay, I wrote the other order, but the second one is cryptographic. Okay, so what is cryptographic fairness? Okay, cryptographic fairness says, in simple terms, that after running this protocol, either the exchange was successful, meaning that they received the exchanged outputs on the end, or they simply retained their original data, meaning it's an all or nothing guarantee. Either everyone exchanges, everyone is happy with what they got, or they just didn't do anything, they retained whatever they had before. So it can't be the case that one of them learns and the other one didn't. So that's a violation of fairness, or a cryptographic fairness. Okay, well, then what is game theoretic fairness? Game theoretic fairness says that the honest party in this protocol, right? Sorry, the honest behavior, meaning that the honest, the protocol specification, following the protocol specification is honest behavior. So honest behavior is incentivized. So if there is an user who's considering deviating and forming its own strategy, there are incentives in place that's going to incentivize this user to take the honest protocol specification, and that's like game theoretic fairness. Okay. All right. So for the rest of the talk, I'll be focusing, the emphasis is going to be on fairness, and security and privacy are equally important, but there are going to be techniques in place that will help us achieve those. So I won't be talking about security and privacy too much today. Okay, so such simple fair exchanges have, I mean, it's fundamental. We have been so used to running complex applications that we forget that a fair exchange is the most basic form of an operation in an application, right? So you start with, like payment applications. Like, for example, Alice has a payment and Bob has some data. They want to exchange. That's a fair exchange. Now Bob could be having a service, a cloud computing service or a cloud storage service, or again, that is a fair exchange, right? Then you have outside the payment setting, you have contract signing. So you have like two users. Think of your HelloSign or DocuSign, where you have like the grant agency and yourself signing the document at the same time. So the fairness is that, okay, either both get both signatures on the document or none of them do. So that's again a fair exchange. And more complex scenarios where the fairness definition is a bit more involved are scenarios where the two parties are trying to generate a truly random number together, right? So the fairness there talks about what are the properties of the random number that they generate. Like one of them should not have more control over the random number, meaning the party should not be able to bias or predict the random number. So it has to be completely unpredictable and completely unbiased. So as so there are several, many more two-party exchange scenarios where that show up in several distributed applications and in real life, honestly. Yeah. Okay, so there's a clean result from several decades ago from Cleve that says that if you do not have an honest majority, you do not get you simply do not get the cryptographic fairness that you want. All right, and clearly in a two-party case, you do not have an honest majority. If one is corrupt, it's 50%. So you need 51% of honest parties. Right. Okay. So given this negative result from Cleve, over the years, the community has explored various relaxations of fairness, right? So one such relaxation is game theoretic relaxations, where you say you model the adversary not as any possible computing machine, but rather as a machine or a player that's going to behave rationally, right? Meaning the adversary is going to deviate from the honest behavior only if the deviation is going to give it a better utility than behaving honestly. So it's you assume the adversary is going to be rational. Okay, so that's one relaxation, and we have many works and many different fairness notions that explore that setting. The other one, the lesser known one, is to limit the computing power of the adversary. All right. So one such relaxation is what is called as depth bounded adversary or bounded PRAM adversary. Right. So this adversary is something that you say we can use arbitrary amount of parallel computing power, but it cannot run, after some time. So it's for example, think of it as a machine that can only run for 2 hours. That's it. It can use arbitrary parallel computing power, but it can only run for 2 hours. So if you have such depth bounded or bounded parallel running time adversaries, we know that some notions of fairness are actually possible. Okay, so yeah, so the point of this is to say that the ideal strong fairness, while is impossible, there are interesting and meaningful relaxations of fairness that have been studied and that have been implemented, and that those are the ones that are actually in use. Okay, so today we will be restricting ourselves to the payment setting. Given the broad interest of many members here and also my own research interest, so this seemed appropriate. Yeah, so we'll focus on, even within the payment setting, we will simply focus on a case where Alice has a payment, Bob has some data, and Bob is trying to sell the data, and Alice is trying to obtain the payment if and only if, Alice is going to pay Bob if and only if the data is transferred to Alice. Okay. All right. Okay. So yeah. So unconditionally, we know from Cleve that this is impossible. So we are obviously going for some relaxation. And this relaxation is something that's that's going to be facilitated by a public ledger. And by public ledger, a simple instantiation of that is a blockchain. Okay. Just a short primer on blockchain is that it's you know we should forget all properties or whatever, consensus and everything. We are not going to make use of that. What we really want is a public ledger where people can post messages and people can read messages. And you want some guarantee about non-tamperable storage on this. ledger, right? So for all purposes, it can just be a bulletin board. So if you have a different instantiation that's other than blockchain, we are still good. But for now and for ease of understanding, we are just going to use a blockchain. All right. Okay. And how does this? And we want a blockchain system where people can use it as a means of payment, right? So here, if Alice wants to make a payment, right? Alice prepares a transaction, which in future slides I would be calling the message. So this transaction has some context. So it's going to pay from Alice to Bob. So some public key to some public key. And this transaction or the message is going to be posted onto the blockchain. Because it's public, if anybody can read this message. And yeah, and this once this is published, we consider the payment to be done to Bob, because Bob can subsequently post his own transactions that will spend, right? All right. So to do this fair exchange of data, all right, you can use blockchain-based payments. And the simple way to do this is to use what is called a hash time lock contract, which is otherwise also called a HTLC. Okay, so here what's happening is that you have Alice who wants to pay, and Bob has the secret. All right. So what Bob does is Bob generates a short hash digest of the secret, gives the hash value to Alice privately. So all of this is private communication. What Alice does is Alice sets up a contract, right? You can think of the contract as a message. The contract says that if Bob is able to give the pre-image of this particular hash value before some time, then transfer the money from the public key of Alice to the public key of Bob. This is the contract. Okay, and this is also this is called hash time lock contract because there is a time lock here to ensure that the money of Alice is not locked indefinitely into this contract. Because if Bob doesn't show up with the pre-image, the money would be locked in the contract forever. So that shouldn't happen. Therefore, you have a time lock. Okay. All right. So this contract as a message is posted onto the blockchain. It's public. Anybody can read it. Now, what Bob does is Bob can also post, right? So it's a public ledger. So Bob posts the pre-image onto the ledger, right? And the users of this ledger or this blockchain can check, okay, this is the contract, this is the data. You check, you hash the data, you check if it's equal to the hash value. It's done. So the contract is considered executed and the money is instantaneously considered to be held now by Bob. You can notice that this is atomic, right? Because the instant that Bob publishes the pre-image, at the same instant, the money is considered transferred to Bob. And because it's a public ledger, Alice can read off the ledger and learn the corresponding data. It's a simple exchange for a simple data exchange for a payment. Okay. All right. So this HTLC-based exchange is quite fundamental to many other applications that are running on blockchains. I won't be going into the details, but you can feel free to check it out. They are implemented today, and they are in use for various applications and various use cases, actually. All right. So one question that we have here is that we are using some form of a special contract, right? This is called this hash time lock contract. The question is, can we do without that, right? And why do we want to do that? Is because you have three fundamental reasons. The first one is that you're leaking unnecessary information on the chain, okay? Because possibly every other message that's getting posted on this ledger is just going to be some arbitrary message that may not have the context that this special contract has, right? So that's already a leak of information. And we know that there have been, heuristic analysis or clustering techniques where, you look at this ledger, it's public, right? So you look at this ledger, you're able to group certain messages together and learn, information, unintended information about the users involved in those applications. So So yeah, for the interest of privacy, this is bad to use these special contracts. The second one is to execute the contract, you have to pay the price. All right. It doesn't come for free. So unlike a regular message that has the minimal form of cryptographic authentication, which is just verifying a digital signature, this contract has additional context. You have to like take the data, hash the data, check equality, and then you read the contract piece of code that says transfer the money and so on. So it has a different verification procedure entirely, and it has its price. It's not the standard one, right? And finally, the thing is, you need now, for doing this data exchange, you need a system where the ledger should support such contracts, right? So you should be able to post such messages, and the users of the ledger or the users of the blockchain should be able to execute the contract, right? Not just treat it as any other message, but they need to execute the context of the contract. So you need additional capabilities from your underlying ledger. And clearly now, if you have a data exchange that's built on top of these hash time block contracts, you're not compatible across a wide array of ledgers or systems that maybe you want to use for different reasons, but now you can't because those systems do not support these contracts. Okay, so it's basically privacy, cost, and compatibility, right? Okay, so these are some of the reasons why we want to move away from using these special contracts. And the question is, can we place optimal trust on this additional assumption of this ledger? Like, what does this mean? Leak the bare minimal information that you must to facilitate the exchange. And the second one is to ensure that you are scaling much better than before, because if you have to execute these complex contracts, that's going to take both cost and it's also going to take money. So it's going to affect how many of those contracts you're going to run. So make sure that you are using minimal use of such special operations to ensure that you can do more, you can support more applications. And finally, can you build on top of any ledger system, right? That only offers minimal support, right? To just, it says, okay, post a message, I will verify the authentication, that whatever you using, I will verify a digital signature. This is the minimum that I'm going to offer. Okay. Now, yeah. So the question is, yeah, can we build these data exchanges by optimizing the trust, in optimizing both in terms of the level of trust you place and as well as the amount of interaction that you have with the trust source. All right. So there is a cryptographic tool called adapter signature. Some of you may be familiar with that already. For those of you who are not familiar, it's a cryptographic tool that's built on top of a regular digital signature scheme. Okay. So a signature scheme allows you to generate keys, a signing key and a public key. It lets you sign using the signing key on a message. So from here on, whenever I say message, you have to think of it as a payment transaction. Okay, it's a payment transaction paying from Alice to Bob. So from now on, that's the message. Okay, and then you can publicly verify a signature. So this tool called adapter signatures is built with respect to a given digital signature. So let's assume that we are given this digital signature, whatever the algorithm may be, this is what we're given. And this is the signature scheme that's going to be used to authenticate messages on this ledger. Okay. Okay, so now what is this adapter signature scheme, right? Now, I said it's built with respect to a digital signature scheme, right? Now it's also going to take what is called a hard relation. All right. So so it's basically an NP relation where the capital Y is the statement and the small y is the witness. In plain terms, you should think of capital Y as an advertisement from Bob, saying that here I have some data that I want to sell. It satisfies some properties. That's capital Y. The small y is actually the data. Okay. We want this hard relation. What is the hardness here? Given capital Y, meaning given the advertisement, it should be hard to compute the data, right? If it is easy, there's no point selling. So given capital Y, given the statement, it should be hard to compute the corresponding witness. Okay, so these are the two objects that you want, and with respect to which you are going to build this tool called adapter signatures that's going to facilitate this optimal trust data exchange. Okay, good. Okay, so this adapter signatures has 4 interfaces. Okay, so the first one is called the P sign or the pre-signature generation. All right, so what does this do? This is run by Alice, right? So Alice takes her signing key, the message, and the advertisement and generates a pre-signature. This pre-signature is not yet a valid signature, right? It's just one step away from being a valid signature, but it's not yet a valid signature. Okay, so then you have a pre-verification algorithm that's going to allow verifying a pre-signature, right? Whether it's well formed or not. That's fine. That's fine. Then you have what is called an adapt algorithm. This adapt algorithm is going to take this pre-signature and it's going to take the witness and it's going to transform the pre-signature or adapt this pre-signature into a valid signature. That's what adapt does. And then you have the extract algorithm that's going to take the pre-signature and a signature, and it's going to efficiently extract the witness that was used to adapt. Okay, so what's happening is, in the next slide, I will show you how this facilitates fair exchange. But yeah, you have pre-sign, adapt, and extract, right? And a key property that we want is whenever you adapt a pre-signature into a signature, that adapted signature must be verifiable using your verification algorithm of your digital signature scheme. Or in other words, when you adapt, you should not require a new signature verification algorithm. You should be able to use the old one or the legacy one that the system offers. Okay, good. Okay, so how is this useful for a fair exchange? Okay, so what's happening is Bob wants a signature on the payment transaction, while Alice wants the witness of the statement, meaning the small y. That's what Alice wants. So what happens is, okay, Bob gives the advertisement, which is capital Y, and this message, the payment transaction. Alice generates a pre-signature on this message and gives the pre-signature to Bob. What Bob does is Bob adapts the pre-signature using the witness that he has and publishes the message and the signature on the ledger. So notice that it's a simple message, no context, nothing. It's just a public key to public key message. And there's a signature on that. Okay, so for anyone verifying a message and a signature, it's going to be valid. And the whatever the payment is considered transferred to Bob. Okay. Now, because this is public, that's why the public is really crucial. So because this is public, Alice can actually extract. So first of all, Alice can read the signature because it's public, right? And Alice can locally run the extract algorithm. Because Alice was the one who generated the pre-signature, it can read the sigma from the ledger, and it can locally extract and get the witness. So you see this nice circle forming here that allows you to do a fair exchange without any use of any special contract. Okay, any questions? Yeah, that's all you want. Yeah. Okay. All right. So there's one additional point. We want this time lock property still, because that is something that you can't get away with. Because if Bob disappears, you don't want the money to be locked forever. Alice's money to be locked forever. So this is otherwise called dropout resilience. And yeah, so that is something that we additionally need to take care, but I won't be focusing on that because there are some standard techniques to do that. Okay, and in subsequent works, we actually strengthen this property. We say that even if Bob is doing arbitrary deviation, colluding with, what if Bob is able to, in some sense, up to a limit, compromise the ledger itself, do we still have fairness and so on? Okay, so those are stronger models that we consider in follow-up works. But here, yeah, here we just deal with dropout resilience. Okay, so what are the advantages of this adapter signature-based fair exchange is that you have minimal interaction outside, right? So all you give away is a message and a signature, no contract, no nothing, right? And in the end, it's going to be a simple signature verification. That's efficient. That's a bare minimum you want from a authenticated system. So it's efficient. You should read fungibility as otherwise as privacy, because you're not leaking any information, saying that it's a special contract. No, that information is gone. And you get better compatibility with systems, right? Because when you build this ledger system or this blockchain system, a signature authentication is minimal. So that's going to be available everywhere. So you can build your data exchange on top of any system that has signature authentication. Good. All right. So yeah, there are numerous applications that have been built on top of adapter signatures. On the theoretical side, there will be new constructions of adapter signatures that have like post-quantum security. And recently, there are also like stronger definitions that were proposed, security definitions that were proposed for adapter signatures. Because when adapter signatures came out, there were only like a few known applications. And all the security definitions of adapters were tailored for those applications. But over the years, new applications started coming out, and the old definitions were found insufficient. So you really needed stronger definitions. So that was done in this 2022 work. That's also done. That's also something that I will briefly touch upon. We also did enhance the definitions a bit more. Okay. Yeah, so basically limited, the security formalization was limited to some applications. That was a problem. The second issue, when even if this adapters was, seemed quite useful, there are some limitations. So one of that is that until our work, the known constructions of adapter signatures were only for certain signature schemes. Right? So if your signature scheme that you're using for authentication was something like a Schnorr signature like, only then you could build adapter signatures. That was a limitation, right? And there's something called, it was limited in its functionality. That is something that I will briefly touch upon if I have time at the end of the talk, okay? That's another recent work of ours that I'm very excited. Yeah, okay, so we want to overcome these problems, like limited compatibility. You want better definitions, and you want to expand the limited functionality as well. So, so these are the key questions that we have, and I'm just going to deal with the model and new constructions first, and then later, if I have time, I'll talk about the functionality expansion. Okay, so we had like two works. The first one was Eurocrypt this year. I don't know if anyone was there for the session. And the second one, if anyone is going to CCS, they can feel free to drop in. Okay, so I will talk about the first one first. I will also kind of, depending on the time, yeah, I will. All right. Okay, so there'll be some slides that I'll walk through a bit faster, just in the interest of time. But I know that many of you may be interested, so please ask questions. I'm happy to deal with them offline as well. Okay, so this is like the standard Schnorr signature, and first we will try to take some inspiration from the existing constructions of adapters, right? So this is the standard Schnorr, and the way you have this hard relation. And then what you do is, okay, you build on top of this signature scheme. And the key point to note here is that when you do this pre-signature, it is structurally very similar to the signing algorithm. But notice that there is one component missing here, right? So essentially, the pre-signature implicitly computes this value, which is the correct signature is sigma 1, sigma 2, but what it computes implicitly is sigma 1, sigma 2 minus y. So there's this small y component missing, and if only you had that, you would be able to add it and complete it into sigma 1, sigma 2, which is the valid signature. That's all you need to take away from this construction here. Okay, so that's what adapt does. So adapt is something that you can only run if you know the witness. That's run by Bob, who is a seller. So what Bob does is just simply adds that to the second component and completes a signature. And you can easily see how the extract is done, right? So because now, given the pre-signature and the signature, right, you just you take the second components of your pre-signature and the signature, just subtract it, and you get small y. It's a simple it's a simple arithmetic operation. There's no complex cryptography involved in adapt and extract. Everything is taken care by the structure of your signature scheme. That's why the structure of your signature scheme is quite powerful. Whatever happens on top of that is quite simple. So this is like Schnorr adapters. Okay, we are trying to, what we try to do is take some inspiration from this, and the abstraction that we had was that some form of a homomorphic one-way function was required, because so if you see, why did you need the small y here was because the capital Y was involved in the first component. So you needed the capital Y in the first one. That meant that you need the small y in the second one. So there's some form of a relation, right? And and we call that a homomorphic one-way function. So the structure of your signature scheme needed to have this. The second one is the Schnorr adapters, right? They heavily relied on this particular hash function here. That was kind of letting the security analysis of this scheme go through. But we found that actually the hash function is actually not necessary. It's a sufficient one for Schnorr adapters, but it's not necessary to build new constructions. So these two observations helped us in defining a new abstraction called dichotomic signatures. Okay, so what is this? What is this dichotomic signatures? We say that a signature scheme is dichotomic if it satisfies some structural properties, these three specifically. Okay, the first one, it says that, okay, it's a two-component signature, and it has this given this appropriate inputs, you can define functions that will generate the first component independently and the second component independently. So that's why it's called decomposability. The second one is we want some, this homomorphic one-way function would show up here. So we want some homomorphic in the randomness used in the signing algorithm. Okay, so you can see it here, right? So this the small y is outside the function, and if you homomorphically add it, it is equal as if that the small y was part of the randomness originally. Okay, and finally, something you need about verifiability, but that's not that's just a very tiny detail for the proofs to go through, but not very important. Okay, so yeah, sorry. You really wanted it to be modeled as the ROM. But so you needed that. So even for the proofs of your adapter signatures to go through, you had to simulate your random oracle that was used in your underlying signature scheme. So it's not like because your underlying signature scheme used it, that's why you're using it. No, because to have consistent query responses for pre-sign and sign, you had to program them. Like for example, the adversary could query the pre-sign, but you don't know if it's going to query the sign later. So you had to, have a random response for pre-sign and later reprogram it when the same message was queried for the sign. So to ensure that consistency, you really needed to program the random oracle. Yeah. Okay. So the takeaway from here is that if you have a signature scheme that satisfies these three properties, then it falls under the class of dichotomic signatures. And if it's a dichotomic signature, we say you can build adapters on top of that. So, and this dichotomic abstraction, right? This structural abstraction of dichotomic signatures is strictly larger than whatever we knew before. That was building things out of ID-based signature schemes. So, or in other words, Schnorr-like signatures. So this is strictly broader than Schnorr-like. Now it captures all the Schnorr-like and additionally a few more signatures. Yeah, so Schnorr falls under this category. That's what this one shows. This is fine. And yeah, I'm going to skip this slide. This is if someone is interested, I can. This just shows how you build adapters for dichotomic, but it's very similar to how you do it for Schnorr. Okay, so there are, as I said, I promised that there are more signatures that will fall under this class. So these are some of those. So you have this BBS plus signatures and CL plus signatures are signature schemes that have nice properties that could be used, for example, in anonymous credentials, right? And you have this water signature that that was one of the first signature schemes that it was not relying on any heuristic assumptions. Yeah, so these three fall under this new dichotomic signature abstraction. Okay. Yeah, this just shows that those signatures are dichotomic, and this slide here was like a generic compiler. So if you had a dichotomic, you can build adapter generically. That's what this shows. Okay. Okay, so in terms of security, also in our work, we identified like these stronger notions that you want, and all of these notions are tailored, keeping fairness in mind. Okay, so the first one is unforgeability. That says that even if Alice gives this pre-signature to Bob, if Bob did not have the witness, right, Bob should not be able to forge a signature of Alice. That's a fairness requirement. And then you have witness extractability that says that if a valid pre-signature was given by Alice and Bob is able to publish a signature on the chain, Alice should be able to extract a valid witness. That's a fairness, again, requirement for Alice. And then you have adaptability that says, given a valid pre-signature and a valid witness, right? Bob should be able to get a valid payment or a valid signature on the message. Again, a fairness requirement. Okay, so one thing about adapters is this primitive, unfortunately, is kind of locked towards this fairness. So maybe there are other applications of that. Yeah, if you think about it, yeah, happy to discuss. All right. So yeah. So as I was just telling Mohammed there, we do not have the luxury of these heuristic hash functions. So you can't play around, with some easy tricks that you could do with the proof analysis. So we needed to come up with some new ideas to prove that the dichotomic adapters are secure, because you don't necessarily, those signature schemes that you saw, BBS plus, CL plus, and Waters, they do not have that hash function, and we do not want to introduce a hash function additionally. So yeah, so we had to like prove the security from scratch with new techniques, and that is something we call as transparent reductions. Yeah, before without going into too much details, the idea is when you want to show that your adapter signatures is secure, typically in all the previous constructions, the way you would do it is you would say, if your underlying signature scheme was secure, your adapter signature scheme was secure for whatever definition. Okay, so that meant that you would build a reduction proof where this adversary A was the adversary against your adapters, and you would build a reduction that would use this adversary and break the security of your signature scheme. So that's what the reduction would do. Okay, But we are not able to do that anymore because we do not have this programmable hash function anymore. So what we had to do was, whatever you see within this LO space here, that's actually the code of the reduction of the signature scheme's security. So your underlying signature scheme will have a proof of security, and that means that that will have a reduction proof, right? So this proof will say if some underlying hard problem, if some underlying problem was hard, then your signature scheme was secure. So for that statement, you would be having a reduction. So what we did was we took that reduction code, we made non-black box use of that reduction and plugged that here, right? This A is still an adapter adversary. That's fine, that's fine. But this yellow thing here is actually the reduction code of your of the security analysis of your underlying signature scheme. So what this meant was that our theorem statement is something like, if your signature scheme had some properties of transparent reductions, right, then our adapter signature scheme is secure, assuming the hardness of some underlying hard problem, right? So we do not directly reduce to the security of your signature scheme, but we reduce to the security, we reduce to the hardness of the problem underlying your signature scheme. All right. So for that, we needed to make non-black box use of the reduction proofs. So that's another technique that we had in this work that could be of use for other tools as well. Okay. Yeah, I encourage the cryptographers, if they have not already, to check out. And if you have any comments, I'm happy to talk about that. Okay, so yeah, just putting everything together. I've given a very, very high level overview. Is that we introduced this new abstraction of dichotomic signatures that would allow you to build adapters for a broader class of signature schemes. We introduced this transparent reduction technique that would allow the proving the security of this broader abstraction. And yes, and also we saw some new schemes that potentially fall under this bracket of dichotomic signatures. Okay, in the last part, I just want to briefly touch upon how to what does it mean to expanding functionality. So if you notice this, when you have this adapter signatures, when Alice does the extraction, it fully extracts the witness, which is, in other words, the small y. Okay, so what if the advertisement was something like, I have a employee database of, I don't know, million employees and their entire details. Okay, this is the advertisement, and the data that Alice is interested in buying is maybe just an entry of one of the employees, right? So it could be just one data point, right? Clearly, Bob does not want to give the entire database because adapters would allow full extraction. So you do not want to give the entire database. You only want to give some entry of the database. So there is this granularity that is missing from adapter signatures. Okay. So in general, yeah, the fonts are messed up. In general, what if Alice has a function f and Alice wants to learn f of y? Right? Not just y, but f of y. And you can think of this to be useful in, like, this f could be like an aggregate function, like maybe computing mean, computing some statistical operations over this data that Bob has, or it could be, this f could be an ML model. Like, so Bob could be holding some data and Alice wants to run a model and refine, maybe train the model on the data that Bob has and refine its model. So it wants to learn f of y. So yeah, it could be an ML. So Bob could be like, I don't know, could be offering a data availability service for ML models, right? That's what this does. Okay, so so for this, in this new work, we introduced this tool called functional adapter signatures. Okay, so it's the same as before, with the addition that the pre-signature is generated with respect to the function f. And when you do the extraction, it's a functional extraction where given the pre-signature and the signature, you're able to extract f of y and not y. this is the interface. So the interface is is similar to what we had before. Okay, so again the fonts are messed up. Apologies for that. And more than the adapter signature security, you want one additional property here, right? So that is called witness privacy. What is witness privacy? It ensures that Alice does not learn more than what she is supposed to learn. Okay, so the most intuitive definition is witness hiding. That says that if Alice learns f of y, which she should not be able to learn y. Okay, so that's witness hiding. That's like a very intuitive definition. But we want something stronger, right? We want to ensure that Alice learns f of y and nothing more, right? Not like few bits of y or some information about y. Nothing more than f of y should be revealed, right? So that's very similar to the zero knowledge secure privacy notion of zero knowledge proofs, if you have heard. So that's the zero knowledge notion of witness privacy for functional adapters. Okay. In subsequent slides, I have the construction itself, but I don't think I will have time to go over that. But what was interesting really when we were doing this is when we were trying to build it, right? So the template that we used was to use what is called a functional encryption and a standard adapter signature scheme. So we use these two tools to build functional adapters. Okay, so what is very interesting here is that this functional encryption is this all-powerful encryption scheme. It's a very classical tool that has been studied for like a decade or more. Okay, and it's a theoretical cryptographic tool. Right now, we were able to see that okay, this tool and this old tool, relatively old tool, and this adapter signature, which is like fairly new, it's like a couple of years old, both of them just combined, they at least intuitively, they look like they were match made for each other. Okay, but once you look closely, it's not what it seemed to be. You needed you needed a lot of care, but you found this amazing connection between something like a classical cryptographic tool and adapter signatures, right? That's a fairly new cryptographic tool. So in this work, what we do is we take a functional encryption that supports functions of like degree 1 or like linear functions, right? So this f is linear in its input, right? So if we take this linear functional encryption and your adapter signatures that you may have today, we are able to build functional adapter signatures that support linear functions. Linear functions meaning inner product, right? So that still would allow you to do weighted sums and means and averages and kernels and whatnot. Good. Yeah, so yeah, this is, I'm not going to go into these details. What do I have? Just a point. So how is this FE? If anyone is familiar with FE, the way it is being used is that Bob encrypts the data using the functional encryption. And the functionality of the functional encryption is that if you had access to what is called a functional secret key, you're able to learn the function of the message that was encrypted, not the message itself. So you can decrypt f of m, where m is encrypted. When you do this decryption, you learn f of m and not m. So that's the functional encryption. So the idea here was that Bob would encrypt using the functional encryption would encrypt the data. And what is in sale, what is being sold is the functional secret key. To sell the functional secret key, you would use the adapter signature. So what you really wanted was this functional secret key had to be compatible with your adapter signature. That's where the challenge really was. And we found that, okay, it can be made compatible if you do some, if you involve yourself a little bit here. Okay, so all right. So the first half was mostly motivating fair exchange and the need to have optimal trust and to convince you that cryptography allows you to have optimal trust. The second half was to show you that okay, we can actually build new constructions, make it compatible with the existing systems with broader class of systems. And there's this new tool called functional adapter signatures that allows you to go beyond all or nothing payment for data, right? It's like, I get all your data. No, you're going beyond that. You get more fine-tuned sale of information or functional sale of information. Okay, so we are actually trying to pursue these open directions, but for people here, we do not have satisfactory solutions yet. In fact, we do not have any solution for going beyond linear function. There are some clues, but nothing as clean as what we had for linear functions. You need to do some additional interaction to go beyond linear into quadratic and cubic and so on, but nothing as clean as linear. So maybe if anyone is interested in that, that's something that we could look at. New applications of FAS. So adaptive signatures, when it was originally introduced, it was just for fair exchange. But then people realized that it's useful for a lot of blockchain applications. So for us with functional adapters, it's now we are starting at the square one. We are saying you can do functional sale of information with two parties, but maybe you can do many more things with multiple parties, right? So that's something to explore. And in terms of minimal assumptions, I didn't go into the details of what assumptions we needed, but that is always a direction that I think cryptographers will be interested in. I can talk about that later. Okay, all right. And these are some of my other works that can be put into different categories. So this is just an advertisement for myself. I'm acting like Bob here. So if any of you are interested in talking about these other areas or brainstorm some questions, I'm happy to talk with you. All right. Yeah, that's about it. I think I tried to keep time, but yeah.
Thank you, Aravinda, for the interesting talk. So may I know if there is any question here?
Yeah, thank you, Sri, for the nice talk. So I have a few questions. So the first one is, when you introduce the adapter signature, so you introduce this hard relation that you said can be used to hide the data, right? But the example you showed us is using just discrete exponentiation to hide the little y, right? But can your constructions work also with a commitment to y, so it does?
I wanted to save you some work. Okay, so okay, you can do that. A straightforward approach is the following: whatever data you have, whatever relation that you have, you encrypt the witness, okay, where the encryption key and the decryption key share that exponentiation relation, and you sell the decryption key for that. This works right off the bat. But there are problems here where this new relation that you may have could be arbitrary. It could be an arbitrary NP relation. And when you encrypt this witness, you not only encrypt, but you also have to prove that the encryption is well formed, right? So when you have this arbitrary relation, that proof will blow up. So we are now looking. So one of our directions that we are exploring is to build an adapter signature scheme that works for arbitrary NP relations without having the seller to prove over this NP relation. That's something that we are exploring, and it seems like you need like really heavy tools of cryptography to come in, like indistinguishability obfuscation or garble circuits or something like that. That really shows up immediately, or FHE, and not R and FHE. So you really need the heavyweights to come in. Yeah.
Yeah, for the general construction, the generalized construction of adapter signature. So you mentioned that you are making non-black box use of the reduction algorithms of the original scheme. So do you also need to make any assumptions about the reduction algorithm, or does it work for any?
Yeah, they need to. So there are properties of the transparent reduction. So that I didn't list those. So there are like it needs to have what is called we call as a simulatability of signatures. So that's so if the reduction of your signature scheme had that property, and the signature scheme had the dichotomic construction. So those two things,
Oh, okay.
then we do that.
So you'd still need some additional properties.
Because we are making non-black box use of the reduction also has to have some
Okay,
this
yeah.
transparent property.
Okay, but you show that this holds
Right.
for some. Okay.
Yeah, it was not fully refined, but
Okay, yeah, thank you. And for your functional adapter signature, do you also need some special conditions? Because you said that it only works when you somehow match the adapter
Yes,
to the.
yeah. So it's not a generic construction. It's not a generic construction for any linear FE and any adapter. It doesn't work that way.
Right.
It only works for a specific few, not one, but few candidates of FE and.
Oh, okay. Okay. All right. Yeah. Thank you.
The problem with compatibility really showed up because we wanted to get the zero knowledge witness privacy. The strongest notion of witness privacy was the reason we really needed that additional restrictions. If we went for witness hiding, for example, if your relation, you only cared about hiding Y, right?
Yeah.
Few bits of Y, if you're fine with that.
Yeah.
If you're fine with that, then you don't have the problem with this compatibility.
Okay.
Yeah, you get a much broader class of construction.
Yeah. All right. Thank you. Yeah, that's all from me. Thanks.
May I know any other question?
Hi. Thanks for your talk. So my question is where you consider sort of homomorphic properties in the adapter signature, that means ECDSA won't be applied there, right?
No, you can make it to work with easy. So the homomorphism is not like it's for a specific component in the signature. So it's for the randomness that you use for your signatures, right? So I think for ECDSA you need to do something different. It doesn't fall under this ID based signature scheme.
Yeah.
So they do something different, and that's very ad hoc to ECDSA.
Yeah.
So we didn't really focus on that.
Yeah, structurally, that's a little bit difficult to do that. Yeah, that's right. And another question I want to ask is like about the fairness. You mentioned here, let's say Alice paid to Bob, and you have this fairness in the signature. But consider back to blockchain, then that means when Bob published the signature, maybe someone, Alice can also like create another transaction, fork the branch, and then make the UTXO go away.
A simple trick that you can use here is if you make the key to be if it's a multi-signature, right? So make it a 2 out of 2 key, so the pre-signature becomes an interactive version. That would immediately fix the problem, and it doesn't add any new security complexity.
So that means at least you need that blockchain to support this kind of like multi-signature wallet, or
as I said, so it could be 2 public keys, seller buyer. Then you would need the blockchain to support like verification of 2 signatures. Or what I'm saying is it can simply be a single public key where the secret key is shared between the buyer and the seller. Right? Yeah. Then the blockchain, you don't require anything additional from the blockchain. It only verifies a single signature. But your pre-signature becomes more complex.
Yeah.
That's happening off-chain.
Yeah. Yeah, I know. Yeah. But if that is the case, then you have the problem of locking the coins. If Bob goes away.
The locking of the coins has to happen whether you share the key or you have multi-signature. Locking of the coin has to happen.
Mhm.
Yeah.
Yeah.
Because you needed this proper resilience.
Yeah, yeah.
The one that you said.
Yeah.
You need that anyway.
Yeah. Okay. Thank you.
Any other question? No, let me just have a look from the online. Okay, seems there is no other question. Thank you.